This presentation is part of the TI-Nfocus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2017 AP Calculus exam, free response question AB3 BC3. My name is Steve Kokoska, and I'm a professor at Bloomsburg University in Pennsylvania. I'm the former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. I'll focus on the solutions presented in these guidelines, not how the points were awarded. Now, even though this question was not calculator active, I'll consider some solutions using technology. Using technology to solve these problems, numerically and/or graphically, can provide additional understanding and comprehension of some important calculus concepts. And because the free response questions are usually very comprehensive, I'll suggest some problem extensions, additional AP Calculus type questions associated with the information given in the problem. And some of these extensions may be calculator active. In this problem, the function f is differentiable on a closed interval, and we know that it satisfies the initial condition f of minus 2 is equal to 7. The graph of f prime is given in this figure, and it consists of a semicircle and 3 line segments. In part A, we need to find the values of f of minus 6 and f of 5. In part B, we're asked to find the intervals on which f is increasing. In part C, we need to find the absolute minimum value of f on this closed interval. In part D, we need to evaluate f double prime of minus 5 and f double prime of 3, or to explain why the value does not exist. Here's a quick look at the scoring standard used at the AP Calculus reading. And remember, I'm going to focus here on the solutions, not how the points were awarded. Part A was worth 3 points. The solution presented involves the fundamental theorem of calculus, or with a rearrangement of terms, some call this the net change theorem. The definite integrals in the solution are evaluated by interpreting these expressions as net area. That is, the area bounded by the graph of f prime above the x-axis minus the area bounded by the graph of f prime below the x-axis. Part B was worth 2 points. And in order to solve this problem, we need to find the intervals on which f prime of x is greater than 0 by examining the given graph. Note that the intervals on the scoring standard do include the endpoints, but I want to remind you that inclusion or exclusion of the endpoints doesn't matter for scoring, but by strict definition, the endpoints should be included. Part C was worth 2 points, and the solution presented involves an appropriate table of values of the function f. We evaluate f at the critical values and at the endpoints of the closed interval. We then select the absolute minimum value of f from this table. Part D was worth 2 points, and we can find f double prime of minus 5 by computing the slope of the line segment that makes up part of the graph of f prime. And to show f double prime of 3 doesn't exist, we need to consider the analytic definition of the derivative. And in this case, that means we need to examine 2 one-sided limits. Now I want to remind you that many students in this problem resorted to a geometric description instead. And some explanations were acceptable, but others were just too vague. Here are some technology solutions and problem extensions. Remember that this free response question was not calculator active, but we can use technology to support and confirm our analytical answers and to explore other possible problems. In Part A, we can use the given graph to find an analytical definition for f prime of x, which will be a piecewise defined function. We can find the slope of each line segment and a point on the line. We can then find the equation of each line using the point-slope formula, and that gives us 3 pieces of f prime of x. Then we need to use the equation of a circle centered at the origin with radius 2. Solve this equation for y, and use the negative square root since we need that part of the circle below the x-axis. Using the TI-Nspire, I defined the function f prime, and then I produced a graph just to make sure that it looks like the one given in this problem. Using the calculator function fp, which is the analytic definition of f prime, and the fundamental theorem of calculus, or the net change theorem, I can find the values for f of minus 6 and f of 5. In particular, notice that the value for f of 5 is the exact symbolic answer. I can also visualize and confirm these results by graphing f prime and using the technology to compute the area of each region. In part B, I can actually use technology to find the intervals on which f prime of x is greater than 0. I used the solve command and the calculator function fp. Now, this solution requires some conceptual understanding, but only a straightforward interpretation of the given graph. But it's nice to confirm this observation using technology. The graph of f is increasing on the intervals minus 6 to minus 2 and 2 to 5. Here are some problem extensions that are loosely associated with part B. First, on what intervals is f decreasing? Well, I can certainly examine the graph of f prime, but I can also answer this question very quickly using technology. I used the solve command once again to find those values where f prime of x is less than 0. And I found that f is decreasing on the interval minus 2 to 2. Let's see if we can find the open intervals on which the graph of f is concave up, the open intervals on which the graph is concave down, and let's see if we can find the points of inflection on the graph of f. I need to find those values where f prime is increasing and those values where f prime is decreasing. So I started out by using technology and the solve command once again, and here are the resulting intervals. A traditional way to solve this problem analytically is to create a sign chart, but I can actually use technology to create, well, almost a sign chart. And here's the interval on which f prime is greater than 0, and here are the intervals on which f prime is less than 0. Here are the solutions to this problem extension. And remember that a sign chart alone is not sufficient justification on the AP Calculus exam. So note that I've used appropriate AP Calculus language, interpretations of my sign chart. In part C, I need to know where the absolute minimum value can occur. I can then use technology to create a table of values. And I started with a formal definition of the function f. First, on the home screen, I found the value of f at each critical point and at the endpoints. But I can also create a table of values on the TI-Nspire in a Lists and Spreadsheets page. And if I need to, I can also convert the symbolic answers to numerical approximations, just to make it a little bit easier to select the absolute minimum value. I think a nice extension to this problem is to ask for a graph of the function f, given the initial condition in the graph of f prime. Well, this is very easy to produce using technology. Here's a graph of the function f and the function f prime on the same coordinate axes. And an additional question would be to describe the relationship between these two graphs. Here are a few more AP Calculus type problem extensions. For each of the functions defined below, find the domain and range, the intervals on which the graph of the function is increasing or decreasing, find the intervals on which the graph of the function is concave up or concave down, find the inflection points on the graph of each function, and finally, find the absolute extreme values for each function. I think that students can solve each of these questions analytically, but they should also be able to use technology to explore and confirm their results. In Part D, I can start by using technology to find the values for f double prime of minus 5 and f double prime of 3. I used the derivative template to find the derivative of f prime, and I evaluated the result at -5, and the answer is -1/2. I tried to use the same method to find f double prime of 3, and here the calculator returns undefined. I need to do a little bit more graphical exploration to see why f double prime of 3 is undefined. We know that if a function is differentiable at a value a, then its graph can be made to appear locally linear near a. So I started with a graph of f prime, and I zoomed in near the point 3,2. My window settings are given in the screenshot on the right. There's a sharp corner in the graph of f prime at the point 3,2. And no matter how far I zoom in, I cannot make the graph of f prime appear to be locally linear. So graphically, f double prime of 3 does not exist. Now, this doesn't replace the analytical justification, but it does lead to some acceptable geometric explanations for the reason f double prime of 3 does not exist. I hope this video gives you some good ideas for additional practice AP Calculus exam type questions, and of how to use technology to solve some of the parts of this problem, and to explore, confirm, and visualize results. And just a reminder, there are lots of valuable resources on the TI website. There is material there involving technology, of course, calculus, classroom activities, and lots of calculator tips and tricks for test success.